what? The example that's on the screen is going to help you for number 7 and for number 25. Because number 7b is an angle not expressly on your unit circle, and number 25 is an angle not expressly on your unit circle. However, the unit circle can still be used. But how? Kiddos, where is 9 pi over 4?
Oh, it's where pi over 4.
How do you know that, though, Jackson?
Because I counted.
What do you mean you counted?
7 pi over 4. So if 8 pi over 8 is, or 4 pi, or like
8 pi over 4.
8 pi over 4
is 2 pi.
Then you just add 1.
Ooh.
Yeah.
So they're thinking about a calzone, actually 2 calzones that have been cut into fourths, right? 1, 2, 3, 4, that's pi, and then 1, 2, 3, 4, that's another pi.
Yes.
So there's 8 slices total if we're cutting them into fourths.
Yeah.
And so if it's 9 pi over 4, that's 1 pass. 8 pi over 4. So they went an entire 2 pi or 8 pi over 4 and said there's one more. So you actually have 2 whole calzones and another fourth. Look at you guys go. But just because it's bigger doesn't mean that it's not still, remember, a bigger angle just has you rotating more. If it has you rotating more, you're just going to land on one of the old-fashioned angles. And what's the old-fashioned angle? Pi over 4. It's a coterminal angle. It's landing on pi over 4. So therefore, if I'm looking for sine, add a pi over 4, which is a 45. And if you guys remember that our coordinates just count in the sense of this guy is, wait a minute, I counted backwards. That's awkward. Cosine actually is the x, and the x starts off being the biggest over here at pi over 6. So the biggest would be, or I should say the biggest would be right down here at 0, 1, right? 1, 0. The cosine would be 1, the sine would be 0. And then the cosine or the x is a little bit less here. So root 3 over 2, but still the bigger one. And sine is, well, it was the smallest, now it's the smaller. And then when I go to the 45, now the cosine has been dialed back to the middle, and the sine has grown to the middle. Have you guys noticed what's always going to be true at all of the 45s or all of the fourths all around the circle? We didn't talk about geometry last time, but guys, what happens if I have the 2 sides of the triangle being congruent? What kind of triangle has 2 sides that are congruent? Do you remember from geometry?
45, 45, 90.
45, 45, 90. It's also known as it's a special type of isosceles triangle. Right. But the 45, 45, 90, they're going to have the exact same side lengths. And the exact same side lengths is only going to be that middle ratio. Do you guys remember? There was the smallest, smaller, middle, bigger, and then the biggest. And they had these patterns last time. But anyway, long story short, as soon as you figure out the first quadrant, sine is positive in the first quadrant, root 2 over 2, booyah, there he is. Are there patterns as far as how you connect or how you label your unit circle? Yeah, totally. Those are the examples that we did. Sorry, I meant to go to the one here. There are patterns as far as the x starts the biggest and then counts down by those special 5 numbers that we talked about. Sine starts at the smallest because y is 0 and counts up through those 5 numbers. And then what was this for? What was I talking about that I labeled like these little
quadrants?
Yeah, the different quadrants, and these are ordered pairs, right? What am I showing? The x values are all positive, good. The y values are all positive. So the x's are, wait, which trig function or which trig ratio? The x's are my, oh, it's in your notes. You guys wrote a whole table. Yeah, cosine, right? So my cosines are positive and the y's are my sines. And so if we go back to that original table, in the first quadrant, ooh, this might be helpful. In the first quadrant, my x's are positive, my y's are positive. Why does that mean that all of the trig functions are positive? There are 6 different trig functions. So how can I say that all are positive in the first quadrant just by knowing the x and just by knowing the y? What does tangent use? Oh, so what's a positive over a positive? Still positive. What's cosecant use?
A 1.
Flipping the y, right? Reciprocating the y. So reciprocating the y, that's still going to be positive. Reciprocating a positive, still positive. Reciprocating the y over x to be x over y, still positive. All are positive in the first quadrant. Question, what's a generic ordered pair? What are the signs going to be in the second quadrant? What becomes negative? Start from the origin, move there. What's negative in the second quadrant? The x is negative, the y is still up, right? So question, who's going to be positive in the second quadrant? The y or anything dependent only on the y. So sine and his reciprocal. But we shorten it just to say sine. But sine or his reciprocal. So the main three and their reciprocals, sine and his reciprocal. How about quadrant 3? Move there from the origin. What are the signs of the points?
Negative.
Negative because left and negative because down. So therefore, who's going to be positive?
Cosine and sine.
Nope.
Oh wait. Oh, positive.
Only tangent because what's a negative over a negative? So out of the main three, tangent and his reciprocal, aka cotangent. And then quadrant 4, move there. Who's negative? The x is positive, the y is negative, so which trig is going to be positive? Cosine and his reciprocal. So from last year, yes, this might be a great thing to write in your notes, whether on the quadrants or in the unit circle itself. But last year when we said all students take, we shout out to Mr. Crawford, but that was a long time ago. You guys might have had him come in chapel one year and play the guitar. Mr. Strike's friend, but he taught Algebra 2 here for a long time. All students take, I loved his phrase because he said calculus, and I was like, yeah, they could if they applied themselves. But if you guys don't like that, you could also say chemistry because I think actually all people take that. But even then, there might be some exceptions. If you want to say all students take classes, okay, fine. But either way, all students take calculus or all students take classes. What am I trying to remind you? Starting in quadrant 1, who's positive? All three in their reciprocals. In quadrant 2, who's positive?
Students.
What does it mean? I mean, hopefully you're positive people. That'd be great. But sine is positive in his reciprocal. Whose sine's reciprocal? No.
Wait, I'm sorry.
Sine's reciprocal?
Cosecant.
Cosecant. Do you guys see there's only one s in each, right? Or there's only one co in each? Cotangent is the co-function of tangent. Cosine's co-function is secant. Sine's co-function is cosecant. Anyway, only one co per pair. Sine and cosecant. All students take. What does that stand for? Tangent and his reciprocal cotangent. And then classes, cosine and his reciprocal. There's already a co. He must be the secant. Anyway, that's just a reminder as to who's positive, who's negative. Why? Well, because we're starting to summarize this unit circle guy and try to get you guys faster. Sorry, we're trying to summarize this unit circle guy and trying to get you guys faster. So in the first quadrant, all are positive, sweet. As soon as I see he's a 45, 45, 45, 90, that should put me in the middle, right here. And all are positive, so I don't even have to think about it. I don't even have to draw it in some senses. Now let's go look at your homework questions, because they kind of came off of this, right? You guys were asking for determining coterminal angles. We just had a coterminal angle for pi over 4. They gave it to us, but just because they gave it to us doesn't mean that we can't make them ourselves. What would be another angle that would land on 2 pi over 3?
8 pi.
And how did you get that? Well, coterminal, it's always going to be some sort of whole multiple of 2 pi away. And that could be a plus or a minus. So if I want to add 2 pi, hey, my guys in the back, what would 2 pi be in terms of thirds?
Oh, I got you.
How many thirds would that be? Mm-hmm.
Yeah,
6 pi over 3, right?
Yes.
If I want to think about a whole rotation in terms of thirds, there would be 6 of those thirds. That is 2 pi. So 2 pi plus 6 pi, that would be 8 pi over 3. That's great, but they don't just want a positive. You guys read the directions, right? What else do they want?
Negative.
The negative. So what happens if I do 2 pi minus 6 pi, both over 3?
Negative 4.
But why was letter B a little bit harder?
Because you have to use it like multiple times.
Yeah, because they give me a negative 9 pi over 4, which, do you guys remember, wasn't 9 pi over 4 more than a full rotation? So they've gone, like, they've really spun it negatively. They spun it like a whole rotation and a little bit more. So I could go ahead and add, wait a minute, you guys told me what was 2 pi in terms of fourths again?
Oh.
8 pi over 4?
Yeah.
Good. So we could add 8 pi over 4, but that just gets us back to the first negative variation, right?
Do it again.
I do it again, exactly. I could have my first one and then I could go again. Actually, let me just wait and we'll use it then. Just keep going. You just need to keep spinning until you get positive. You'll get positive if you go one more. I say rotation. I should probably be saying revolution, which is an entire rotation. But then you get your 2 of negative pi over 4 and 7 pi over 4. I would love to say that there is a formula. Actually, there is one. I've given it to you. You can find any coterminal angle alpha by starting with beta and then adding multiples of 2 pi. Adding or subtracting, but the problem is you still need to, technically that's for all n within the integers, but integers 1, 2, 3, 0, 1, 2, 3, 4, no fractions. But you have to apply the understanding in order to realize, oh, just add it again, no big deal. Like you just need to keep rotating because you're not quite positive yet. Okay, that was number 7. That wasn't unit circle, but that was coterminal, which was what we were dealing with in the first example. Let's go down to 25, where this one was actually having us find trig, but find trig at a coterminal angle, or find trig at an angle that's not expressly in the unit circle. But guys, the unit circle is meant to be a tool that you use, not something that you only memorize. Do you guys know the difference? If you only memorize it, all you can do is I ask and you answer and you're done. But in the higher classes you're taking, aren't you supposed to be able to apply the knowledge that you're learning? Right? Like, is it just regurgitating facts? No. Hopefully not. So we actually want to use the knowledge that we have. Anyway, 13 pi over 2, look in your unit circle. I know it's not there, but use the knowledge that you have. A circle, you spin, it's positive, you're spinning positively. Guys, what is 2 pi in terms of halves?
4 pi over 2.
Yeah, exactly, 4 pi over 2, right? So what does it take for me to do an entire revolution? 4 pi over 2. Well, how many 4 pi over 2s do I have? I have 4 pi over 2,
3.
I have 8 pi over 2, I have 12 pi over 2,
And 1.
and one more. Oh. Now, could you do some sort of formula thing? Yeah, I guess so. I mean, I guess you could do like a 13 pi, you could do divided by 4, and then you would end up with 3 and 1/4 over 2, and then it starts to get really awkward, right? Or you could do things like you could try to take away the coterminal angles or take away the extra or the spare revolutions. So you could do like 13 pi over 2 and say take away 2 pi. Ew, that's awkward though. Why not use what we're doing in terms of getting a full revolution with a common denominator in terms of the same number of slices that you're referencing? So then we could subtract 4 pi over 2, but it's still going to have some extra, so that would still be 9, minus 4 would still be 5, minus another 4 would be, oh, finally, I would get to pi over 2, which is exactly, like there is some formulaic way of taking away the multiples of 2 pi that are there. Or just spin, 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 spin until you land at, well, there I am. What's happening here? Well, cosine started at its biggest and has now made its way to its smallest, which is 0. Sine started at its smallest and grew to its biggest, which is 1. And what are they asking for specifically? Sine, which is the y. If you guys want to think about it, you can call it siney. It's the cute little sine. Why? Because it's a sine with a y, kind of like Dominix and Rangy. Rangy is the one with the y. It's the cute little siney. Kind of awkward, but it works. There's a pretty easy one as far as remembering the cosine, but I'm not going to really go there. This isn't a bio class. Joey?
When I watched the watch it for the secant 1.8, I plugged in what the dude put in, and I got something completely different.
Secant of,
It was like 1.8.
oh, that's gonna be an awkward calculator one, because 1.8 isn't, right, I mean, secant of 1.8. It's like what we're doing here in the terms of there is no degree mark, so it is in radian mode, just like this is. It's just awkward because it doesn't have a pi in it, so it's not going to be like a nice answer. So then you would just want in your calculator, you guys know in mode that there's two different options, right? Uh-huh. And so you would need to go ahead and make sure that you're in radian mode, number one. But number two, you would also need to remember who secant is, because there is no secant button. Now some of you were like, ooh, but there's a cosine with a -1 by it. And the struggle is, that little -1, guys, it can mean reciprocal, right? First of all, hold on, let me model. My function or my calculator is in radian mode, so that's okay. Some of you might have been trying to be clever and say, yay! But here's the struggle. If I plug this in, it's going to get really mad at me. And it's going to say that it's impossible, that it's outside the domain. But here's the weird thing. What if I was to do cosine of 1.8, and then I was to do the, oh, where is it? Hold on. Here it is. And I was to do the -1 button. Some of you thought that these mean the same thing, but they don't. Do you know why?
To the cosine of the 1.8.
Well, here's the weird thing. This notation on the inside does mean powers of trig usually. Like if it was cosine squared, it would be the same as a squared there. If it was cosine cubed, it would be the same as a cubed there. But this is a -1 on the inside, and in math, in context, these are defined to be, which is why we haven't gone over them yet. This is defined to be cosine backwards. Do you remember what that word is? Some of you might have said it already. What's cosine backwards?
Secant.
No. Cosine reciprocated, flipped, is secant. That's this guy.
So,
Cosine backwards is cosine, starts with an I and ends with a verse. Inverse.
Oh, wait, inverse.
Remember F inverse of x? Backwards is undoing. Square to square root, ln to e. 10 to the a common log. All of those undo. This little -1 has multiple meanings in math. And so for us to realize, for you to realize, these little guys above sine and cosine and tangent are inverses, just like the guys above ln and log and squared. Do you see? Look at your calculator. Above squared is a square root. That's not reciprocal, that's inverse. Above common log is 10 to the. That's not reciprocal, that's inverse. Above ln is an e to the. That's an inverse. Above sine and cosine and tangent are inverses. So therefore, if you want to do secant, my best advice is actually just to go ahead and do 1 over, use the definition of secant, which is 1 over cosine, which is what you have. Is that cool, Joey?
Yes.
Yeah. Super common mistake right here at the beginning of trig. Now, kiddos, we do need to go ahead and get back into, that's not what I wanted to do. We already covered 25. Let's get back into notes. Specifically, let's go talk about some geometry, because hopefully geometry helps solidify just some of the stuff that we've already been doing, and this homework isn't meant to be too crazy. As far as our, let me pause the recording. Yeah, I should have already filled in some of the geometry stuff, like, okay, this guy's going to be opposite. This guy's going to, wait. Careful. With the unit circle, guys, we are specifically always talking about the angle that's in here by and formed with the origin. We're never talking about the outside one because of the standard position until we start applying this. But for unit circle, we're always talking about the inside one, the one drawn to the x-axis, the standard position angle. Okay, so we have opposite there, we have adjacent here, and we have hypotenuse here. Are you guys good if I use O for opposite, A for adjacent, and H for hypotenuse? You know that's not a 0, you know that's an O. How about your friends that are really struggling with staying awake today? So we have so, ka, oa. And what's this guy again? Oh. Sha. Oh. Couldn't this also be a reminder of so and cho go together? Sine and cosecant. Ka and sha go together? Cosine and secant. And then toa, I almost said backwards, toa and kao. Tangent and cotangent. But anyway, you do have your shortcuts reminder that most people do that remind you, that could remind you. But once again, I was trying to not use a lot of geometry last time so that we can come in and use geometry this time. Geometry like, don't we also have special reference angles within our first quadrant of pi over 4s, pi over 6s, and pi over 3s? And how does that correspond to degrees? Pi over 4 is half a 90, half a pi over 2, that's going to be a 45, right? Pi over 6 and pi over 3, they're just different orientations of, pi over 6 is 1/6 of 90, no, sorry, 1/3 of 90. And pi over 3, that's 1/3 of 180. I have my 30, I kind of like the 1/6 of 180 thing better than the 90. And then 1/3 of 180, that's 60. What do these relate to in geometry, if we're going there? What are those two special triangles again, guys?
30,
45,
60,
45, 90,
90.
and 30, 60, 90.
And which one is isosceles?
The one with 45.
And doesn't isosceles mean they're congruent?
Yes.
And so doesn't that one have to be the one where, well, usually it'd be a 1, 1, root 2, and you'd have some a's and stuff. But if we divide everything by root 2, to scale it back, because that's way too big for a unit circle only goes out 1, I have to scale it back, and to scale it back, I divide everything by the exact same factor. Do you see where root 2 over 2 comes from? There he is, with the hypotenuse of 1. That's where those come from geometrically. That's where those numbers come from geometrically, not just some trick, but actually how it works. A 30/60 says, which would be like the pi over 6, right? A 30/60 is a 1, 2, root 3 triangle. Usually in geometry you guys had a's or x's or something and you solved with special ratios, but for our purposes, once again, that would be outside the unit circle. I need to scale it back. I need a hypotenuse or a radius of 1. So scale it back, scale it back, scale it back. Okay, that's where everything comes from. Root 3 over 2 is my x, 1/2 is my y for my little triangle, but if we flip it for the other guy, then it's 1/2 and root 3 over 2. Ryan?
So is that what it kind of like rotates within like increments of like square root of 2 and then like square root of 3 for the 36?
Because everything, like if you were to take these triangles and like flip them, wouldn't they fit in with all the other fourths and all the other sixths and all the other thirds?
Yeah.
Yeah. Exactly. So technically the geometry says, hey, these special triangles, they're still at work in this thing called the unit circle. Now what if you were given, oh, my theta's got, it's okay. Just pretend they're there. I'll write them in. How are they going to force me to use geometry besides just making it, I don't know, a way to remember some of those numbers a little bit better that we already saw last time? Well, they might also give us something like this. And they might say, hey, sine of theta is equal to 0.6. Find cosine and tangent. And you're like, but I need my calculator and I need the inverse button and I need theta and I need, no you don't. You don't need any of that. Why? Because trig gives you ratios. Guys, what did you just say sine of theta was equal to? Opposite over hypotenuse of a right triangle. So can't we say in this one that 0.6 or 6 over 10 corresponds to is some sort of ratio of an opposite over a hypotenuse? I don't know how big this triangle is, but I know the ratios of its sides, its opposite and its hypotenuse. So therefore I should be able to at least have a similar triangle to the actual one, with an opposite of 6 and a hypotenuse of 10, and using those two, which I could have done 3/5 and used 3 and 5 as well. I'm just trying to get the ratio right. I don't know the exact size, because this could have been reduced from something, but Can't I figure out a corresponding adjacent and use it for whatever they want me to?
Yes.
How do I do that? Well, what's the most fundamental theorem that relates the sides of a right triangle? Pythagorean theorem. A squared adjacent squared, sure, plus 6 squared is equal to 10 squared. So therefore, A is equal to, let's keep it positive unless they tell us to go into a different quadrant. Otherwise, we'll assume it's quadrant 1. Okay, dangerous. A little bit of assumption going on. We'll assume it's like the most standard possible triangle ever, and we don't care about quadrants. So what's 100 minus 36, everybody? Starts with a 6 and ends with a 4. 64, that has a square root of? Nice. So how are they asking me to find cosine? Well, I should be able to know that cosine is 0.8 with a little bit of deduction. And then tangent is 6 over 8, that's 3 over 4. Oh, isn't that 0.75? But let me do little reminders like 8 over 10, just in case you're wondering where this comes from. And like 6 over 8 or 3/4. Once again, where this comes from. I don't know the size of the original triangle per se, but I do know what the ratios will be, and that's exactly what it's asking for. Ryan, go.
Okay, would it be plus or minus 8 because like it's a side, so like it can't really have like a negative one?
Yeah, we're just kind of assuming unless or until they give us more information, which they do when it's necessary. They'll give us like a, hey, it's between pi over 2 and pi. And you're like, oh, different quadrant makes somebody negative. They'll have to give you that extra information. Good call. But for right now, we're just kind of keeping it geometric. So, as we already talked about, if you guys didn't write it down yet, if you didn't, then go ahead and write down those special angles if they're a thing. If you did, you're totally fine, except, are you thinking of them strictly in terms of degree, or are you forcing your brain to relate them to radians? Believe me, your brain needs the forcing and it needs the extra practice, but if you have not yet reviewed this or written this, just remember I have 1a, and root 2a if you want those special ratios. And then we do have isosceles, so those are always the ones where we have the exact same order pairs, the root 2 over 2s, because of the geometric principles. And then this one, I'm just writing one. You guys can flip it and write the other one as well. But that was the 1a and the 2a and the root 3a, which careful, the root ends there. But if you want those ratios, but that's exactly where we get, once again, those special numbers of 1/2, root 2 over 2, root 3 over 2. That's what happens when you take adjacent over hypotenuse, an adjacent over a hypotenuse, an opposite over a hypotenuse, or an opposite over a hypotenuse, an adjacent over a hypotenuse, when rationalized. But then you can also think of some things like, hey, what would happen if I were to take like a tangent of 30 degrees? Well, a tangent, an opposite over an adjacent would be a 1 over root 3, which rationalizes, multiplying top and bottom by root 3. It's another special number that doesn't show up in the main 5, because the other of the main 5 are just if it's on an axis, smallest or biggest. But tangent being root 3 over 3, that's another special one. Or flipping that, cotangent of 30, flipping 1 over root 3 to be adjacent over opposite. So square root of 3 is now a special one. Root 3 over 3 is a special one. We could also look at like cosecant and secant. Cosecant flipping sine, which would be hypotenuse over opposite. That's going to be a 2. Or secant. Now I'm just showing you one variation, but guys, this can happen like in opposite orders at 60 degrees, etc. But there are some other special numbers that do come out of the unit circle. Let's see, hypotenuse over adjacent, which rationalized. And so even though having these main 5 are good for sines and cosines, and they can all be used for the rest, it might be helpful to recognize some other special numbers might be happening as well. Ryan?
So when we're doing the tan of 30 degrees, or tangent of 30 degrees, would we assume that the A is like equal to 1?
Well, actually, it doesn't really matter because when we divide, the a's will reduce away.
Oh, okay.
And that's kind of why the unit circle works for any size circle, because it's just the ratios.
Okay.
Does that make sense, kind of?
Yeah.
Good question, though. So then, guys, these relationships, they're called the fundamental properties, the fundamental trig identities. They're going to come back. We're going to use them again in Chapter 5. This is just their very beginning idea of it. I've been giving you these ideas without expressly saying them, but these are very important formulas that show up again and again and again. So let's not take time to write them right now. You guys take a picture and guarantee me that you'll have it as part of homework written in your notes by next time. Let's not, unless you think you can do it, but I don't think you can. I don't think you can. But sine is 1 over cosecant, or the one we're more familiar with, cosecant is 1 over sine, etc., etc. We do have some other special ones, but the Pythagoreans, the quotients, the reciprocals, there are these relationships because they all come back to a right triangle. And the coolest of which is probably this one, where, like we said last section, sine is the y value of a unit circle when the radius is 1. Cosine is the x value. So why is this one called the Pythagorean identity?
Because they're squares.
Cosine squared plus sine squared is 1 squared. That is the Pythagorean theorem just applied to a right triangle. So that's kind of fun and whatnot. Kiddos, did we get all the way through? No. But what comes next is one of my favorites, and my algebraic people, you might love it if you like any part of chapter 3, because we're just going to be like plugging and chugging stuff and saying like, oh hey, look, it works. Last year you might have hated it. This year maybe it won't be that bad because it's not as scary and you're seeing it again. So we get to play with math and trig and say, you know what, these guys have some special relationships. And so therefore more complicated expressions that sometimes look nasty can be simplified to not be all that bad. Because then if I do one other replacement with that big table that you guys are going to write into your notes and we're going to practice, oh my goodness, you mean to say that this whole thing just becomes a 1? How cool is that? And that whole thing becomes a 1? So if they kind of like naturally occur in some sort of formula or equation or physics thing, maybe I don't have to do all the work of plugging in when sometimes it just becomes something else entirely before I plug in. So there are a little bit of like word problems that might show up. Anyway, guys, you are trying to get 4.1 and 4.2 done by 3:30 today. Get into 4.3 where a little bit of geometry, a little bit of like word problem application-y stuff happens. And we'll see how you guys are doing our next full class day, which is not until Wednesday. Scheduled on the board if you need it. Bye, guys. Chapel. I'll see you in there.